Welcome to Lesson 13. In the previous lesson, we studied step responses for first-order systems. Now we move to the second-order lag, a system with two energy storage elements. The damping ratio D determines whether the response is smooth, critically damped, or oscillatory. By the end of this lesson, you will understand all three cases and how pole locations in the S-plane control the behavior. The general second-order lag is described by the ODE. T squared times y double dot plus 2dt times y dot plus y equals k times u. Here, t is the natural time constant, d is the damping ratio, and k is the static gain. Taking the Laplace transform with zero initial conditions gives the transfer function g of s equals k, divided by 1 plus 2 dts plus t squared s squared. The denominator zeros, which are the poles, are s 1, 2 equals 1 over t times negative d plus or minus the square root of d squared minus 1. The value of d determines the pole type. When d is greater than 1, both poles are real and negative, meaning stable. When d equals 1, we get a repeated real pole. When d is between 0 and 1, the poles are complex conjugates. And when d is negative, at least one pole has a positive real part, and the system is unstable. When d is greater than 1, the transfer function factors into two first-order lags. G of s equals k divided by the product of 1 plus t1s times 1 plus t2s. The step response is a sum of two decaying exponentials. There is no oscillation. The output rises smoothly toward k and never overshoots. This is called the aperiodic or overdamped case. The larger d is, the slower the response. When d equals exactly 1, the two poles merge into a double pole at s equals negative 1 over t. The transfer function becomes g of s equals k divided by 1 plus ts, all squared. The step response is y of t equals k times 1 minus 1 plus t over t times e to the negative t over t. This is the fastest non-oscillatory response. It reaches k without overshooting, but just barely. It marks the boundary between overdamped and underdamped behavior. When d is between 0 and 1, the poles become complex conjugates. The step response contains a damped sinusoid. The output oscillates around k with decreasing amplitude. Smaller d means more oscillation and larger overshoot. This underdamped case is the most common in practice because many real systems have some degree of oscillation before settling to their final value. Let us compare all cases on one graph. For d equals 1.5, the overdamped response rises slowly with no oscillation. For d equals 1, the critically damped case is faster but still no overshoot. For d equals 0.7, a slight overshoot appears. For d equals 0.4, stronger oscillation with significant overshoot. For d equals 0.1, heavy oscillation that takes a long time to settle. And for d equals negative 0.1, the system is unstable and the oscillations grow without bound. The damping ratio d is the single most important parameter for second-order systems. The pole locations in the S-plane reveal everything about system behavior. When d is greater than 1, two poles sit on the negative real axis. When d equals 1, they merge into a double pole. When d is less than 1, the poles become complex conjugates, forming an angle with the real axis. This angle equals arccosine of d. Poles in the left half-plane guarantee stability. Poles on the imaginary axis produce sustained oscillation, and poles in the right half-plane cause instability. The further left the poles, the faster the response decays. Let us summarize. The second-order lag has transfer function k over 1 plus 2 dts plus t squared s squared. The damping ratio d controls the character of the response. d greater than 1 gives overdamped behavior with no oscillation. D equals 1 is critically damped, the fastest without overshoot. D less than 1 is underdamped, oscillatory with overshoot. And D less than 0 means instability. The poles in the S-plane directly reveal the system behavior. This understanding is fundamental for controller design. Next, we will study block diagram simplification.